Acid-base dissociation constants are basically just your equilibrium constant with products divided by reactants, but for weak acids Ka and for weak acids Kb. So there's theoretically nothing new to learn here, but it does get quite complex now that we are introducing the pH equations and incorporating this with equilibrium. And so what we have here is the equilibrium equation for a weak acid, and so you've got the products here divided by the reactants, and because these are in equal concentrations, we can just replace that to a H plus, make that a H plus squared. We can times that out there and then take the square root to remove that, and so we can get the hydrogen ion concentration if we know what the equilibrium, the acid dissociation constant is for the acid and the concentration of the acid. Now for these questions here, because the concentration of the dissociation of the weak acid is very, very small, much less than 1, we usually write the assumption that the initial concentration of the acid is the same as the equilibrium. So you'll see in the problems coming up that I've written that there as the assumption to work out the problems. And another thing is the syllabus has written the proton goes to a hydronium ion, which is fine as well. So in a similar fashion with the base dissociation constant, and again I've gone for the Arrhenius, the hydroxide ion coming off, whereas the syllabus has gone more for the proton acceptor, the Bronsted-Lowry. But I think this one's a little bit simpler to write, so I've written that one in there. In the same fashion, these two concentrations are equal, so this doubles up as a squared, and then so you can work down to this to work out what the OH concentration is and therefore the POH. So just two more things. First of all, what the Ka and Kb value mean. So with pH, a large hydrogen ion concentration gave you a small pH value. With this one here, it's very similar. A large Ka value also means the acid is strong. And that is because the Ka value is the products over reactants. That means this number here will be quite small because the acid completely dissociates. And so for strong acids and bases, you expect Kas and Kbs to be greater than 1, whereas for weak acids and bases where the reactants stay the same, very little of this product comes along, and so it's very small. So for weak acids and bases, you expect the Ka and Kb to be less than 1. So I've just written in the numbers. You can see they're enormous here. So we've got like in the millions here or the thousands for these common strong acids, hydrochloric and sulfuric acid. I've written all of these ones in here because this is the ones your syllabus says you need to know are strong acids and strong bases. So all of the group 1 hydroxides, that's 3.6. You can see this one here is just under 1. And the weak acids here, you can see it's negative over 1 million. And so they're quite huge numbers. So anything of a factor of 3, a factor of 1,000, in your calculations you can write off as 0. So you can see with these numbers here, you can write these off as insignificant in certain situations in your assumptions to work out problems in chemistry. There are other calculations also. So this is a weak acid, and that's how the equation works out. The conjugate base, that's how the equation works out. So if you actually times those together, so these two will cancel out, these two will cancel out, and you get this left over. So that's how we get this here. So Ka times Kb is this, which is Kw. So that is a useful thing to have. And by mathematical rules, logs and inverse logs, if you times them together, they actually end up being pluses. So I'm not going to get into the mathematics of it. I'll leave that there if you can accept that the mathematical rule has been proven and we can just work with these calculations. So this is basically what your data book gives you. So you don't have to memorize any of those, and that's most of them. I just think that in order to be able to solve this, you do actually need to know that the number is 10 to the minus 14. And this one here is extremely useful. I think you can get there by doing inverse logs on this. So inverse log to get rid of that and to get rid of that will get you a similar thing, but this is much easier. I don't have an inverse log on my computer calculator, which I'm always using. I don't carry around a scientific calculator, so I need this. It also makes life a lot easier and a lot faster to have that. And this one seems to be missing as well. Maybe the syllabus just thinks it's too easy to have that in there. But just to know, pH and PO plus BOH is 14. So I think these three are necessary, okay? And they're not in your data book. So as you see, we've technically not learnt anything. We just have a stack of equations now that are integrated and interrelated to give you very complex questions. And so I'm just going to go through these two problems at the end. I've just said, look, it's not enough. You need to do lots of complicated, unusual problems and try and work them out yourself before looking. So I've got the data book equations here, and I've got the other ones that I think should be there as well. So this is just one of the questions. Please go to your textbook and other sources to get more. Calculate the pH of a weak acid. If that's the concentration, that's the Ka. And so always write out your formula before you start. That is being implied, so we're only doing monoprotics here. And so the Ka is this. And so I've rearranged it just like I did in the previous slides to get H, turn that into a H+, and so I rearranged that. So I would suggest you just take this formula here and rearrange it rather than having to memorize anything. You can just get it to that. I think some people who like memorizing might memorize another formula. And so the key assumption is that the initial concentration here, because this is 10 to the minus 5, the amount of dissociation is so small that we can say that that's the equilibrium amount also. Okay, so we grab that number and put it in there. And we also, number and put it in there. And then we have the Ka value from over here and put it in here. Grab it in your calculator that gives you the hydrogen ion concentration, and the pH concentration here is also from your data booklet. Sub those numbers in, you should get a pH of 2.7. If we're going to do sig figs, there's only one sig figs here, so they wouldn't do that to you. They'd give you 0.10 at least, and 4.0 if it was a test question, because so you could give a 2.7 answer. Otherwise, you have to round it off to one sig fig, which is 3, which is quite crude. Okay, and so moving on to the next question. So if you're given a 0.2 molar solution of weak base pH 8.4, calculate the Kb. They've given you the equation here, so you know it's monoprotics, and I think extra tricky with di and triprotics. So for this particular one, the formula is here. You can try doing inverse logs and get the same thing. So I've used this to get the hydrogen ion concentration. I've also used this one here, over here. So rearrange that to get the hydrogen ion concentration. Same assumption again, the assumption that the number will be very small, which it is. So we'll have to go back to that. And so that the concentration in equilibrium is the same as the concentration initially. So you've worked out that the hydroxide ion concentration is here. All right, it's just best to assume that this number here, because it is a very weak base, that'll also be the concentration down here. And so sub those numbers in, and there you get your Kb, which is quite a weak base. Okay, so it can get far more, as you can see, there's quite a lot of different equations and you can come from different angles. They could give you any of these values, and you have to sort of work your way to another value. Another thing that can increase the complexity is, say, well, what if I added, 10 mils of 2 molar NaOH to the solution? What would be the pH then? So you'd have to do an equilibrium, a Rice table, so make sure you find some of those as well, and get lots and lots of practice at doing questions that are completely different each time, because it may just be in the exam that they will try and find something left field that's not in textbooks or you have not covered before, to test whether you can really grab all these different equations and come to the answer that they're looking for. Okay,